Hello everyone. We are Team 3, consists of Sangmin Lee, Jungkoo Lee, and Donghyun Kim. My name is Donghyun Kim, and I am the speaker of the first proposal presentation. First, let me start with topic introduction, and then talk about our application plan, and last, I will talk about our improvement plan. We choose this paper, Area Ground Collaborative Sensing, third-person view for teleoperation. I will briefly talk about the content of this paper. In SAR, like search and rescue mission, first-person view teleoperation of unmanned ground vehicle is difficult since it gives less data about the surrounding environment. Therefore, it is known that third-person view can drastically increase teleoperation performance. So, this paper proposed a way that can provide third-person view for unmanned ground vehicle using micro aerial vehicle. It's a drone. In this paper, they use several strategies. Visual surveying strategy is used for micro aerial vehicles to follow unmanned ground vehicle. For visual surveying, this paper proposed a nonlinear model predictive controller, MPC, which is robust under disturbance rejection and better at tracking performance. Model predictive controller MPC on micro aerial vehicle acts to keep the relative position and orientation between micro aerial vehicles and unmanned ground vehicle. For accurate surveying, they used marker on unmanned ground vehicle. Now you may wonder why we choose this teleoperation as a topic. So let me introduce why. Although many technologies have been developed recently, there are many challenges of autonomous driving, such as coping with the accident and autonomous driving in rough and tough area. Therefore, backup options like vehicle teleoperation become a relevant solution for critical scenarios like a disaster like rough terrain. Using one-board cameras, it's a first-person view like picture in the slide is sufficient in easy terrain, but teleoperation task can become cumbersome in challenging terrains where narrow passages or obstacles need to be traversed. So teleoperation with first-person view in rough terrain is challenging. Teleoperation with third-person view gives more visual information about surrounding environment. Moreover, operator can teleoperate more efficiently at narrow road or obstacle areas. Around view, which is in most current cars, as pictures in the slide, has a limitation due to its sensor position. So they are using micro aerial vehicles. It's a drone. Drone is more flexible at various environment recognition because they are flying. So if we want to detect blind spot or large area, drone can reduce number of sensors and sensor cost derived from position flexibility than ground vehicles. With communications, few drones can cover many unmanned ground vehicles.
We are going to replicate the contents of the paper based on ROS and gazebo environment. We adopted ROS because it is the most flexible and powerful framework for writing robot software. Together with ROS, we are going to utilize gazebo and RVs. Gazebo is the physical simulator for ROS. In this simulator, we will form a disaster-like environment for search and rescue mission composed with various obstacles and narrow passes. We are going to run drone and unmanned ground vehicle based on this simulator. RVs is a visualization tool cooperating with ROS and Gazebo system. As on the right bottom of the figure on the right, Orbis can show not only the overall view of the simulation environment, but also sensor data, including camera and LiDAR, can be shown. Therefore, we are going to utilize it to show the acquired image data. For now, as a digression, we are choosing a drone and mobile robot and the sensors that we will utilize on the simulator. For tracking of drone along unmanned ground vehicle, visual servoing technique will be used. The drone will identify either shape of the vehicle or AR marker on the vehicle and utilize the identified data for tracking. And at the lower level for this tracking control, we are going to implement model predictive controller for the drone.
So from now on, I will talk about improvement plan. The shortcoming of the suggested system on the paper is that it only provides top view. However, there must be a proper view for each person and for each surrounding environment during teleoperation. Besides, we thought that simply providing top view for teleoperator might be insufficient for search and rescue mission in such environment. Therefore, we are going to develop a system that can provide image as seen in the viewpoint that people want. Finally, top viewpoint give various benefits for mapping. Using unmanned aerial vehicle for mapping, there are less obstacles for scanning surrounded environment, while vehicle is limited because of first-person view. For example, LiDAR using laser to measure distance, but when large obstacle in front of the vehicle, it cannot detect obstacle like animal or person behind the large object. So we propose drone with attached 3D RGB depth camera and or 60 or 32 channel LiDAR sensor for scanning ground. Using scanned data and drone autometry, we can map the ground area with no obstacle. Finally, user can acquire 2D projected map from 3D map, which is user-friendly viewpoint. This optimal viewpoint can enhance performance for teleoperating unmanned grounded vehicle, usually at complex and hazardous environment. Also, user can define viewpoint which they are comfort to teleoperate unmanned grounded vehicle. Humans switch the viewpoint to comfortable point and acquire 2D project image from the 3D map, which came out from the 3D LiDAR map. Using 3D LiDAR map, if there are other unmanned grounded vehicle, they share the map information and they can be teleported at each viewpoint. This reusable map is more efficient than each unmanned grounded vehicle make a map separately. Finally, we can give better performance for unmanned grounded vehicle and micro air vehicle shared teleoperation by changing user-friendly viewpoint.